Hello everybody and welcome back to Knifemaking Tuesdays. Today we are making progress on the integral. I've got a bunch of things planned. We'll see how much we can get done, squeezed into this video. There's basically two concurrent projects happening in the next little bit. It's making progress on the blade itself, from surface grinding to lapping to eventually cutting the cutting bevels and then sharpening on all that stuff. See how far we get. And then also making the button of the button lock on our Willman. So we're going to dive into that. But before that, everything about manufacturing is a flowing line like this, at least in the development phase. Like, as much as you plan, things always get thrown to the side for a monkey wrench or a different project that's more important, things like that. I'm trying really hard to manage my time and make sure that I'm putting effort into the important things at the right time. But every now and then you get thrown a curveball and you got to deal with that. So we're going to talk about that in a minute. I'll show you what happened. So one of the two things that I want to make on the Willman right now, one of which is the button, and then the other is a way to mount this molybdenum rod. It looks just like a 1/4 inch end mill, but it's made of molybdenum on our Speedio, because currently we're using the Speedio to grind our rasp blades, and we will soon be using it to grind our integral blades. So I'm going to show you guys. We have this table loaded up hard. This is the S500, so it's only 500 millimeters wide, 400 millimeters deep, like 19 inches by less than 16 inches. And we have our Bloom laser over there. We have a 4-pack of Shunk Vero pallets, which can be used individually like this or as a full 4-pack, which is awesome. Like over here, we have our vacuum pallet with 4 pull studs on it. Love that. And then we have the Aroa/MX chuck over here that the Aroa can pallet change in, which fully works now. It works awesome. It's been amazing. So if I want to mount this guy permanently, I can't make a fixture here because that's a non-permanent setup, and I have very little room. You know, I had a thing that mounted it here, but it was kind of awkward. So what I decided on is to mount it basically right here on that T-slot, between here and here, below the surface of this. So I need to make something that spaces it up off the table about 4.5 inches under the surface of that fully, and so that this grinding wheel can basically come in and auto dress against this stick. So basically what you do is, with this stick being mounted, the tool moving, not the stick, but imagine if the stick was stationary. Put my focus in check here. Basically you go like this, and then in a little bit, and then up and down, and then in a little bit, and then up and down, taking off just a few tenths at a time. And that works really well. But we don't currently have a setup to kind of automatically do that. We do it every now and then. And the wear has been holding pretty good. But after grinding a whole bunch of blades and not dressing it, we're starting to see just a little bit of taper right now. Now the way we're using the wheel is in both the down and the up position, so it's kind of wearing evenly on both sides, but ever so slightly. I want the ability to automatically auto dress it at so many minutes. So what happened was, I designed this part and I go to put it on the Willman, and then I go to do a tool change on the Willman, and it's not happy with the tool change. This is an 18-year-old machine, almost 20 years old. Jeez, it's 20 years old now, 2004. It's a 20-year-old machine. And it's really cool how the tool changer is set up. There's a lower rack and there's an upper rack. Right now you can only see tools in the upper rack, but in the back there's some lower rack tools. So what's happening is this, where are we here? This gripper can tool change lower tools no problem, but it is unable to lift on those 2 cylinders up to disengage, to unload or to load an upper tool. So something is preventing this whole carriage from sliding up on those 2 rails. And asking Willman, you know, I was really hoping it's not one of these airlines or some cylinder in the back that has to be replaced. Quick update on the Willman. It's been about a week since I filmed that last little bit. I was able to get it working. What happened was the gripper that is going to put the tool away still thought it had tool 10 in the gripper. I had manually removed it. But the computer still thought tool 10 was in there and tool 10's in the upper rack, so that's why it kept failing, even when I bypassed the valve and just didn't need it. So the guys at Willman taught me how to properly remove that tool from the memory, M92T0, but in the right orientation. That's like a manual tool unload. And then I was able to run tools on the bottom rack all week for the past week. It's been awesome, actually. So any tools that were on the top rack, I moved them down to the bottom rack, renumbered the tools, like it worked. And then the parts that I needed, I ordered them and they did come in. So I got 2 of these fittings at $250 each. Ooh. Parker sure likes their stuff and they make really good stuff. And then I also got another replacement air filter bowl so that they, the other one was cracked anyway. But since the machine kind of functions, I'm no longer in a huge rush to install them. But I will get them installed very soon. Also, I have bad news. In my quest to make, I think I mentioned in the beginning last week when I was filming, I wanted to make this. I wanted to make a dressing stick mount, and I did make it. Made it on the Willman, like I said, the Willman worked, so I used those tools. Turned the whole diameter, faced the end, slotted the slot, milled precision bore on both sides, and then later I will mill a bore down, and then I drilled deep through. But on the Speedio, I made a big mistake. I didn't film it because I didn't want to. Basically, I had it in a vise like this, and I had the touch probe. Let me go grab it. Notice how the touch probe is in my hand, not in the machine. That's part of the story. So I had this in a vise, and I wanted to come down and just probe the center of this part so that I could drill that deep, deep hole all the way down. Except my fault or the machine's fault or the code's fault or I didn't understand the code, whatever, totally my fault. I had it up here and I wanted to probe the OD and it goes, okay, it goes down here and it goes down, 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 and it crashed. I do have a picture of the crash. I'll put it up right now. Oh, that was a painful Friday night. And then here's the cracked, the glass is all cracked. The case is a little dented. It's sitting crooked on the shaft right there, and it's toast. It doesn't, like, it turns on, but it doesn't work anymore. So, yes, many thousands of dollars later, a new one's coming in about a week. Oh, it sucks. So I'm trying to think of what's the takeaway, what's the lesson? Probing is weird. Sometimes it doesn't listen to feed rate override or the rapid override. Sometimes even feed rate override, it doesn't listen. So I didn't have my hand, I didn't push the feed hold button. I don't know. I'm really annoyed that I don't know what I could have done differently to avoid this. And that bugs me. I've used a probe for 10 years on all these machines. This is the second probe I've crashed on the Speedio. So I will now have the third one in the mail. Oh, I hate it. And it's like on a project that I need and I want, but it's not worth it. That wasn't worth busting a many $1,000 probe to do. Whatever. Live and learn, move on. Probe carefully, my friends. So that's that. Just to add one more piece of context to the probing thing. I'm pretty sure I had it up here and I told it to probe 0.1 inch, which on the Mori and on the Kern and on the Willman, I don't know, depending on the probing cycle, 0.1 inch goes down 0.1 and then touches. Whereas I'm pretty sure, and I can't test it till I get the new probe in, I'm pretty sure 0.1 is going down to a Z value of 0.1, which this is, well, it's actually lower, but bottom of the part. So that's why it crashed. That's why it went down, because it was trying to go to 0.1, not just down 0.1. And different macro routines, Bloom versus Renishaw, I just kind of missed the boat there and I got it wrong. I got it wrong. And I should have tested in the middle of space. Not on the part. I should have tested like 4 inches over just to see what happens. And I don't use that probing routine very much. So anyway, that's what happened. The other thing we did this week is I didn't actually do it. The guys did it. So Angelo and Steven, after Sky heat treated them, Angelo and Steven surface ground these on our Okamoto surface grinder. So we did 2 blades. Normally we don't surface grind after heat treat. We do all the surface grinding soft in the beginning. But this blade being weird, we don't have an established process yet. It worked better to surface grind them hard. And then I literally have a note right here that says, let's film lapping. So we're gonna film a little bit and we'll put it in here where we lapped this blade and got it super nice. We didn't, Steven did. So let's jump to Steven, he can explain this process. And now to Steven with the lapping. Okay, here we got my guy Steven, who is our lapping expert. So tell me about lapping. You lapped this one?
So this one was hand finished, but the gist of lapping is this blade is going to sit in between a pod that's pushing weight down on it and a plate that has diamonds conditioned into it.
Okay.
And it's basically just going to kind of float in between there and skim across those diamonds and take off that little layer, but uniformly, let's say.
What's that?
Uniformly.
Yeah. I always think of it like a million little fingernails on the bottom, just kind of scratching material away. But it's like standing on a bed of nails. You know, it's even pressure, but
yeah, even pressure. Exactly.
Yeah. And you're trying to hold like very tight parallelism, thickness, surface finish, all those things come together into your job.
Yep. Yeah, it's a very it's very easy to let things go wrong with lapping.
Yeah.
Very easy.
So I see on the machine right now, you got your DJ Scribbles pods going. So what do you have in the machine right now?
So I'm running rasp blades currently. So there's 8 blades set up into there, 4 in each pod. And like I said, the big plate on the bottom is spinning and that's conditioned with diamonds. And then these 2 pods are lowered on top of the parts, putting pressure down on them. And this black dot kind of kicking around is the slurry. So that's a little mixture of diamonds and...
Oh, just stopped. Perfect.
A little mixture of diamonds and the metal particulate that we're taking off.
Look at that.
A very dirty job, but something's got to get done.
Yeah. And we have these G10 carrier rings that we make. That's for the Norseman. This holds the blades still. And then we have our integral blade. I wanted to see if it would fit inside a Rask outline, just for quick testing, and it does. So this might actually work. And then we have this one here, which is actually properly cut for this blade. So we can get 5, because the blade's so much smaller, we can get 5 at once. All right. So why don't we just surface grind the blades?
So if you just surface grind these blades, the RA is not going to be nice enough for what we want. We want a super smooth feeling knife. So the smoother you get this surface, the better it's going to feel on the drop shot action.
Yeah, like check out the reflective difference. I mean, this is a literal mirror. I can count beard hairs through it. Look at that, I can see them. So when the surface is really well lapped, I mean, it still looks scratchy, but it's nothing near. This is a surface ground finish from our surface grinder, and it's a very good finish, but it's nowhere near lapping. It just takes it to that next level. And like you said, makes the knife a lot smoother, flatter, more consistent, all the things. All right, thanks, Steve. Now you may be asking yourself, why lapping? What is lapping? Well, it's complicated, but basically lapping is a process that we use on that machine right there, our Angus FL24 lapping machine, uses a diamond slurry, like water with diamonds in it pretty much, to grind the surface super, 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 super flat, parallel, flat plane, and with a beautiful reflective surface finish. Like, you can literally see objects in that surface finish. If you zoom in really close under the microscope, you can see scratches, but they're small and shiny, and it just leads to a really, really nice surface. So in our knives, that translates to a smoother knife. And especially with the integral, where I talked about, like, the button is going to be dragging on that surface. I think our lap surfaces, which we do for every blade we make, are going to help that significantly to just make that feel smoother, because I don't want this integral to be like, dude, my uncle, when we were kids, I was a Spyderco guy, Eric was a Benchmade guy. I'm talking like early teenagehood. Eric had a Benchmade, and he also had a CRK TM16. I think this is what I'm thinking of. And our uncle, who was a police officer at the time, used to tease Eric to no end with his squeaky CRKT. And it would go, man, I still remember that. I bet you Eric will too, absolutely. So that teenagehood trauma of knife shaming is probably what built us to grow this business and now make some of the smoothest knives on the planet. Wow, I never put that together. I'm gonna have to tell Eric, that's hilarious. So that's why I have an $80,000 lapping machine and an operator that basically spends half his time lapping, quarter of his time. Anyway, that's hilarious. Did you know that the very first Norseman knife that I made in 2011 was a button lock? And it sucked. The Norseman's come a long way. It's been a frame lock since this knife, since this one. I scrapped the whole button lock idea, went to the frame lock. We've been making the Norseman for like 11 years now. But in this video, in this Knifemaking Tuesday, we're not talking about button locks. We're talking about integral knives. Knives that happen to also be a button lock. Now, the failures that I had on this knife haunt me to this day. This was made in first prototype button lock, November 29th, 2011. Also date everything you make, because now I can look at my first horrible prototype and know this was made in 2011. It's very important. Look at the bevels on this thing. Yuck. This was made on the old Grizzly X2 mill. This side's much better, just different tool path. So yeah, complete failure, complete and utter failure. I didn't fully understand how a button lock is supposed to work. You can see the button moving in the handles there. And in this episode, we're gonna go deep into button lock geometry and making buttons. And basically, it doesn't lock open, and it almost kind of stays closed. I have this little poppy detent right there, but it does not stay open, and there's no stop pins. I thought the button could do it all. It's just completely wrong, but learned a lot. So conceptually, the way that a button lock works is kind of simple, conceptually, like in concept. You have a little tiny spring, and you have a button that usually has, we'll get under the microscope here in a second, but bear with me. The button usually has a vertical, like, alignment shaft, and the business end here is this tapered cone at the bottom. Now what the tapered cone does is it basically, as the blade opens up into the lock position, that spring wants to shoot the button up, and the taper cone, boop, goes into a section in the blade that has a little cutout, so that when the blade opens, that section is revealed and the cone goes up. And kind of the same thing when it's closed. When the blade's closed, you have a little circle that the button can rest up into, so that as the blade comes across, imagine if there's a hole in the blade comes across, a little button goes bloop. Now where it gets tricky is to make this butter smooth, very tight tolerance, very good feel. You know, our knives, even this, my Norseman number 200, from 2014, pretty sure. Yeah, January 2014. Has the Grimsmo feel. It makes noise, it clicks, it's smooth, it drops, it bounces at the bottom if you don't do it right. And it's super buttery smooth. A button lock has a lot more friction because the button's always shooting up, always rubbing against the thing. For our frame lock knives, we have a ceramic detent ball that we grind flat with a diamond grinding wheel, and then we use diamond lapping paste to lap it like super flat to the blade. We don't have those luxuries with a button lock. We have to, I don't know if this is gonna work. I'm kind of mildly freaking out that this is not going to accomplish what I want it to. But in this video, this is the button lock video, let's figure it out. Okay, under the microscope. So I have these 3 buttons that I bought 10 plus years ago, 12 years ago, that were made, I don't know, I bought them from some knife making website. I can't zoom out any more than this, I apologize. But what's interesting is, use my precision pointing stick, toothpick. This one doesn't even have a taper. I thought that was really interesting. This one has a very steep taper. This one has a similarly steep taper. And that's pretty much all it is. So the blade is rubbing on this lower surface when it's in the open position. On the bottom we have a pocket where the spring is going to go. All 3 of these will have a pocket like that. And that's about all there is to it. Not super duper complicated, but the way I want to do it, tight tolerance, good surface finishes, form, profiles, tapers have to be super accurate, and I'm totally making up what those tolerances and shapes need to be. So let's see if I'm right. I'll show you a quick simulation here. So we rough turn the front, groove, finish turn the front, groove, 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 backwards turn that feature, forwards turn that feature, finish turn that feature, rough groove, and then the vise will come in, it'll grab the part, high feed end mill will chop that off, it'll flip the part 90 degrees, and then it will bore the little hole on the inside where the spring will go. And that's it. So theoretically, all these tool paths should work. I don't know, we'll see. Keep in mind, this whole part is about this long and about this big in diameter. It's not big. All right, here we are on the Willman 408 MT. Let's get a nice little camera angle here. And let's see. Going through my mental checklist in my head here. All right, tool change to grooving tool. Cut the end of the bar off. Notice I'm using peck grooving, where it zips down, down, down. With brass you don't have to, but I'm programming this for stainless steel. Pretty hard stainless, so I gotta baby it. Going down, I'm facing the end of the bar, and then I'm coming back up and I'm doing a bit of a radius, 2-inch radius, very gentle. And then I turn the OD to size. Then I come back with the grooving tool. Rough out some clearance. Yeah, in brass you could absolutely do this just in one shot, but stainless likes to really wrap the chips around, so that's a problem. Such a fast tool changer. Notice now how the turning tool is backwards. Before it was facing forwards, so this lets me turn left to right and get the back wall. It's a really cool feature of having a mill turn. And then watch what happens next. It orients the spindle and then it comes back forwards. And now I can turn right to left. And I have two separate offsets, one for forward, one for backwards, so I can fine tune any little oddities in size. It's super cool. So first I do a rough turning. This is where the critical features are, the little taper, the radius. So I do a rough turn and then a finish turn just to make sure it's perfect. So now the button is almost done. Going to do some final rough grooving. Pecking a lot on this operation because in stainless I found that this creates a very long chip that wraps around the part and causes a problem. Alright, now that's where it gets fun. High feed end mill. Vise will come up. Go into the part, grab onto the part, and now the high feed, actually it'll open the collet. The U-axis is starting to pull the vise out. It's pulling the whole bar out. Not the best camera angle. Clamps again, and now the high feed. I love that. Zip, 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 zip. Checking for tool breakage. Yes, the tool is still there. Now the vise lays down. Change my camera angle here. Coming down, facing the end of the bar. The end of the part is sticking up in the vise jaws there. Now I'm coming down with a 93 thou end mill, and I'm just doing a very tight little boring operation. That's it. Chamfer tool. And that's it. Then you'll see the jaws open up. The part, yeah, it did fall. It held there for a second. Goes down the PVC tube into here, and we have a part. Cycle time was 4 minutes 38 seconds. On a Swiss lathe going balls to the walls, you could probably do this thing in like a minute. But that's okay. Totally okay. Under the microscope here, let's take a look at our part. Really good surface finishes, really good blend lines. I mean, everybody's a hero in brass, right? They say that for aluminum too. Brass is such an easy material to make, and it has its purposes. A lot of cool things are made from brass. Ooh, look at that. That back hole is way off center. So that means my G55 orientation work coordinate system is off center in the machine. I know how to fix that. That's easy. That's off by like 5 or 10 thou. Not hard. Also, there's supposed to be a chamfer on this outer edge, and there isn't. I can change that. But everything looks good. Actually, for this first one, I made the face flat, not the radius that I was eventually planning on doing. This way, when it's flat, I can actually mic the thickness and get my tools dialed in. All right, let me dial this in, make a few more parts. All right, back at it with another part. I've actually made quite a few parts, dialing in all the tools, all the tolerances, and let's see what we got here. So this one does have that domed radius face. You can't quite tell. How's my tool center line? Nice. Nice. No little nub in the center of that turning. Let's see, does the first one have a nub? No, the first one, yeah, the first one's got something. It's got something. And then I dialed in the Y-axis on that machine and I got it much better. So you see how the light reflects differently? On the left we have a flat surface, and on the right we have a domed surface. And the LEDs in this microscope shine differently on flat versus dome. It's cool. Okay, let's see, what else we got here? How'd I do on my centering? Much, much better. Oh yes. Still got a small chamfer on the outside. I'll accept it for now, but I'd probably want to make that a little bit bigger. Inside chamfer is fine, maybe even too big. Probably fine. Good, I like it. Precision pointing stick, my toothpick. A bit of a blend line right there. I mean, dude, nobody cares. This doesn't matter. But that's kind of where my finish path starts. All right, looks good. So to put this thing together, I've got these two bearing cages that we made quite a long time ago, probably 2 or 3 years ago. And it's kind of awkward to put it together. Still haven't found like the smoothest, easiest way to do it yet. But it's sort of a combination of just holding the bearings in place. We'll probably 3D print something for production. Because there's these two recessed pockets on the inside of the handle. And how do I get these to go in there and stay? And we don't grease our bearings. But this has worked the few times I've tried to put it together already. It's just kind of awkward. Oh, I can go through the pivot. I never realized that. That makes it a lot easier. And then I can just kind of push them off to the sides. I need another precision poking device. Okay. That might be the way. There's something now to put them. Need better lighting here. I got one in. Maybe if I come up from the bottom, move it over. There we go. That's a bit better. There we go. All right, she's together, feels good. Get my pivot screw, tighten that down. Oh, look at that boy. No blade play. Of course, it's a Grimsmo. Toot toot. So, does the button fit in the hole? It does. The way I've designed this is that when the stop pin's in place, the button doesn't come out. But if you remove this upper stop pin, there's two stop pins. If you remove this upper open pin, the blade can go up more than it should, and that should allow an opening, there it goes, for the button to kind of fall its way down. There. The button is in. I think it's all the way down, but the blade won't move. When the button's all the way down, the blade should drop. I didn't put the spring in, but that's okay. The button is, maybe the body of the button's too long. Like that extra bottom, where it goes from skinny to that bottom shaft, it needs to be lower. Maybe something's bottomed out. Maybe my drilled and reamed hole isn't going as deep as the model is, because that's the thing with designing something in Fusion is everything's perfect in the model. You can give it a nanometer of tolerance, a clearance, and you're like, oh yeah, miles, because you zoom in so much. In the real world, like when you drill a hole, there's a 140-degree bottom to that hole. When you ream it, there's a chamfer on the edge of that reamer, and you can't smash the reamer into the bottom of a drilled hole, otherwise you'll pack up chips. And so maybe my reamed hole is not as deep as I think it is. Okay, that's okay. I might be able to modify the button. Let me think about it. Got my Norseman here. I'm going to try to pry it up. If it doesn't work, I'm not going to post it. Holy cow, it worked. I mean, I knew it would. All right, open the blade slightly more than normal, and button comes right out. Okay. I think my diameters are pretty critical to the hole size. The hole is 136. The shaft is supposed to be 135. A thou of clearance is pretty good. But if this is machined ever so slightly over, or the hole's so slightly under, things like that, things to watch out for. Okay, I need to make a button that's somehow smaller. All right, now we have a brass button with a bunch of tweaks to it. A bit different, bit shorter length, a bit wider inside clearance, and perfect diameter shoulders. So let's see if this thing fits. I've got my spring in there. Fits down nicely. Sweet, sweet. So I push it down, and then I close the blade a little bit more. Okay, now, good. Now I have movement. I'm gonna put in, I lost it. I'm gonna put in my upper stop pin. For now, these are just exactly the same as on our other knives, and then I have a piece of tape that keeps it in place. In the future, these will be threaded in, so they're gonna thread in from the top. But I haven't gotten there yet. Okay, okay. Moment of truth. Does it detent? Ooh, yes. Ooh, that sounds good. Put it right next to the mic here. Ooh, that feels pretty good. Very smooth here too. I was really worried about that. Very, very smooth. Lock up is... Ooh, it locks up. Button raises. All right, that's higher than I want it to go. And there's actually a little bit of vertical blade play. Just a little bit of looseness here. That's fine though. Wow, it works. It works. All right, so it's been a good bit. Ended up going to stainless and starting to make stainless parts, which brought its own series of challenges. Like I said before, everybody's a hero in brass. Stainless, the chips really string around. That was a big problem. You can't have chips strung around your part and have the vise come in and grab it. So I ended up doing a lot more pecking and a lot more just managing. But otherwise, it turned out really good. And in stainless, it feels really smooth too. Now this, I'm using 17.4 pH H900 stainless steel, which is the same steel we use for our pivots, for our stop pins. We use that, we've been using it forever. We use it a lot. We turn a lot of it in the Swiss lathe. So I'm very comfortable turning it. It's 45 Rockwell, so it's hard-ish. It's not like 60 like the blade is, but it's hard enough. Is it going to be hard enough for this purpose? I don't know. I'm kind of getting nervous right now that it's not going to be hard enough. It's a cool material because you can turn it at 45 Rockwell and hold really good tolerance, pretty good tool life. But if it's not hard enough, I was just talking with Saunders this morning on our podcast, The Business of Machining, and he's like, just hard mill it with ceramic inserts or CBN inserts or something. And then we were like, wait, those usually make sparks, and sparks in an oil machine, not a good idea. So I don't know where that's going, but the other option is to choose a different steel, like, I don't know, all kinds of stuff. You could go 440C, you could do some sort of A2, you could do any steel or stainless, machine it soft, and then all little parts, send them out for heat treat or do it ourselves. But then they come back kind of yellow, kind of matte, kind of dull, not so shiny anymore. So we could either hard turn just the face of it to make it pretty, or polish them or something like that. So I'd rather not do that. If I can stick with 17.4, it's literally a one and done part. If not, there's a lot more steps involved. If we use something like A2 or anything like that, then we'd probably get it PVD coated, DLC, something like that, which is cool, but it's a whole nother step. So we'll see. I've been playing with this for a while. Let's take it apart. Let's go under the microscope and we'll see how the button is kind of wearing. I can tell already there's some slop in the open position, some slop in the closed position, because if you're wondering why this blade still has a hole in the tip, it's not done yet. That's all it is to it. We're going to use this for fixturing when we grind the blade bevels, and then at the very end that gets cut off. The whole edge here is about 20 thou thicker, so that's too much, and it's basically hitting back here in the handle, so the blade is not fully closing as much as it will in the future. So if I have time tonight, just depends on how long I want to stay, I want to make a soft blade that is like near net shape, that might still have the tab, but the cutting edge is to shape and it doesn't have all the extra junk that this blade does, so that it actually fits realistically in the handle, because I need to see, if I'm going to start changing tolerances and dimensions of this detent, I need to see where the blade will actually sit. Actually, I wonder if I can measure how much the button is coming up from down, which the pocket on the blade is 15 thou deep. Okay, so this machine pocket is 15 thou, so I'm guessing that this button is going to come in the detent position, is going to raise up 15 thou. The question is, because on my feature I have like a radius and then the taper for the lockup, how much is 15 thou too much? I think it is, because when the blade's closed right now, I cannot flip it open. I think I have too much vertical sidewall engaged in that detent. I need more radius engaged in that detent. So I think I need to make that pocket less deep. And maybe chamfer, like radius the front of it, something like that. These are tight little features, I don't know yet. But it's coming together. And the lockup too, I think I'm gonna have to move the feature. Either I make the button a bigger diameter or I move the locking feature in the blade, arc it over just a little bit. We shall see. All right, under the Zeiss microscope, I want to see how everything's wearing. I want to take a close look at how the button is doing, if it's wearing out, if it's scratching. Let's take a look. Look at the blade first. My spring is stuck inside. Let's poke that guy out. All right, get it on my flat here. Focus is pretty good. Oh, look at all that. Look at that garbage. So the gold is obviously the brass and the silver is the 17.4 stainless. Stuff's wearing out. The brass, obviously the brass is so soft. The stainless, that is a lot of stainless chips that are only coming from the button, which tells me the button is absolutely wearing out and is probably way too soft. You can see ever so slight on this top outer edge, there's a bit of a wear line, which is where the button is rubbing, and that's why it's so smooth, because we have this lapped surface. So I'm really happy with that. Change my lighting around a little bit, maybe we can see a different angle, but not really. Now I want to show you guys how the button interacts with the blade and how it's assembled. Most button lock knives that I have seen have the locking feature on the outside of the blade, a little tapered, divot right on the outside here. I decided to put it on the inside. So we have, where's my pointer? So we have a tapered surface there and a tapered surface there that are at a 3-degree taper. I'm matching an exact 3-degree taper on the side of the button there. And I have this extra oval at the top that is ever so slightly bigger than my button, and that's how we install the button. And then it comes forward, and this is your locking surface. So I have a 3-degree taper matching a 3-degree taper. The jury is still out if they need to be the same, if they need to be slightly different, if 3 degrees is too steep. So imagine 0 degrees, 1 degree, 3 degrees, 10 degrees. A lot of other buttons that I've seen are closer to 10 or more. So 3 is, I don't know, it might get stuck. Imagine if it's 1 degree, ever so slightly, it's just gonna get stuck and it's gonna be hard to disengage. We'll see. So far, it's feeling great. So it assembles like that. The spring goes here in the pocket in the bottom. You push the button, and then the button slides across this lapped surface. That's why it has to be so smooth. And then this is your detent pocket here. We have clearance in the back, so once it's locked into place, clearance in the back because I don't want the back to do anything. And it gives just a bit more place for gunk to go and not be where it doesn't need to be. And basically, spring is holding down the button right here. So as you try to flip the knife, you're trying to force the radius of the bottom of this button, that radius right there, you're trying to force it up and over this ledge in a controlled pop so that it flips out really nice. So the depth of this pocket is pretty critical. The first one I made was way too deep. The second one was maybe a little bit too shallow. So we'll find the Goldilocks right in the middle. And that is how this works. Lock, disengage. 10 p.m. on a Wednesday night in the shop. Kern's still running strong. It'll be running all night. Maury just finished. 10 p.m. on a Wednesday. I'm gonna eat my Korean rice bowl that I found at a little Korean market recently. Not rice, noodle bowl. I don't know what it says, but it looks spicy. That has a kick to it. Wow. First bite in, I'm like, it's not unbearably hot, but it is good and spicy. I like spicy. Okay, check this out. Back at the microscope, remember before when I said that maybe the reamer is shoving crap into the bottom of the hole? While I was inspecting the handle, check this out. This is the bottom of the stop pin hole. I'm no expert, but that looks like a whole bunch of chips that are shoved into the bottom of that hole. Wow. Not sure what to do about that. So that is one of the reasons why sometimes we'll see like a witness mark. There you go. So that's why sometimes you can see that that bump right in front of my finger there. So the hole we were just looking at is this one. Can we see a bump on this side? We can indeed. It's right there. So chips are compacting in the bottom of the hole as it's flowing down. I could poke it again with the drill bit. Doesn't solve the problem. I also have these tools from Harvey Tool called a thread relief cutter. So it goes into the hole, and at the bottom of a bore, it'll make a little like under chamfer. I use these on our handles when we thread mill the holes. I go inside, even for the stop pins go in our Norseman Rask handles. I undercut the bottom of that hole. It just makes everything nicer. But this particular tool is not long enough to reach in the handle. I'm sure they make an extended length one. I might have to do that. All right, guys, I'm gonna wrap it up here. Thank you so much for watching another Knife Making Tuesday, coming with me on the journey. This knife is really starting to come together, and I'll leave you with a little surprise for next week. What is that? Progress, that's what that is. All right, guys, until next time.